Ever look really closely at the fabric on your sleeve? See the pattern, the weave, and the texture. The high-speed loom does it all. Look over your shoulder. A silent spy may be tracking you. The micro drone has moved up from amateur to professional. It's a monster lumberjack. Grab, slice, and stack a bunch at a time. Meet the Feller Buncher. A low-level rescue flight over water, rocks, and land. Speed, turn, stop on command. It's the sports car of hovercrafts. Let's look inside these machines and see how they work. Weaving has been around since the early Stone Age. The basic concept hasn't changed, but speed and sophistication sure have. To keep us all in clothes and bed sheets, we need millions of kilometers of fabric every year. Impossible without the industrial loom. High-speed machines all over the world, like these outside Leeds, England, produce just about anything we need and want. Let's see how they work. First up, the basics. Take 2 sets of threads. The first is called the warp, 2 rows stretched lengthwise. The second set is called the weft, and it goes back and forth between the warp. Every time it goes through, the warp moves to trap the weft. The threads are now becoming a piece of fabric. To keep it from unraveling, a reed pushes the threads together. And then, the whole process starts again. To mass produce a wide range of fabrics, you need to organize thousands of different threads. So, the loom needs a lot of control. And it gets it from these devices called heddles. Each one has an eye through which individual warps are threaded. This gives the machine control of thread movement. Heddles are suspended on the loom's shafts, located here. When a shaft is raised, the heddles go up and the threads with them. To create simple patterns on one of these, you need a few hundred heddles and 2 shafts moving up and down together. Industrial looms have thousands of heddles and up to 24 shafts, all moving independently. That takes care of control. Now let's see how speed works on this machine. To manufacture massive amounts of fabric in a cost-effective manner, the loom needs to rocket the weft through the warp. Old-style looms use a shuttle, a spool of thread that unravels as it moves manually back and forth. Reliable, but slow and in constant need of reloads. This presents 2 challenges for the modern loom: how to weave thread quickly without a shuttle and spool, and how to minimize thread reloading. Enter the rapiers, one of the latest shuttle replacements. One rapier picks up a piece of thread, pulls it to the middle of the warp, and hands it off to its partner. It pulls the thread the rest of the way, while the first goes back for another strand. And because spools no longer have to travel back and forth, the rapiers draw thread from large bobbins. That means a lot fewer pauses for reloading, and this dramatically improves the machine's productivity. On the industrial loom, this handoff happens over 1,000 times a minute. This speed puts tremendous strain on thread snatched off bobbins at up to 250 kilometers per hour. If it breaks, the machine shuts down, and that costs money. So experts came up with a pre-winder, a device that preps thread for the rapier. It's a buffer that eliminates thread-breaking tension on the machine. Another side effect of speed is fabric dust. And to protect workers, it's got to go. Ceiling-mounted vacuums suck up the entire volume of air from the shop every 2 minutes. Okay, the loom is lightning fast, but how does it create different patterns and textures? A geometric pattern, like this plaid, starts with loading the warp with rows of different colored thread. Send a dark thread through the colored rows, you get this. Send a light thread across, you get this. The trick is switching between colors on the fly, and for that, it needs a weft presenter, a component that selects different colors from bobbins and hands them off to the rapiers while they work. For complex patterns, a loom with a jacquard attachment is required. It's a mechanical wonder. The jacquard device controls all the threads loaded into the machine. Instead of ganging them together onto the shafts of a standard loom, every strand has its own control system. So, with a jacquard attachment, operators can control the paths of each thread into ornate designs. Instructions are sent to each individual thread as it races through thousands of weaves. All those tiny decisions add up to a pattern, kind of like how a bunch of pixels become a picture. Its namesake, Joseph Marie Jacquard, invented the first of these mechanical marvels in 1801. Until then, this kind of work had to be done by hand and was extremely expensive. His machine used punch cards to control individual threads, and some consider it the first computer ever built. Which is exactly how its modern descendant works, only electronically. Designs and patterns are programmed into the machine, and away it goes. The threading of a jacquard loom is so labor-intensive, it's usually done just once. When it's time to change colors, new threads are tied on to the existing ones. Even for a small loom with only a few thousand ends, the process can take days. Without these fabric workhorses, the cost of a single suit would leave most of us in last year's deerskin. The loom's a machine to be thankful for. It literally puts the clothes on your back. This is a hovering, unmanned aerial vehicle. The micro-drone MD4-200. Drones like this one are used for jobs like aerial mapping, fire inspection, law enforcement, surveillance, and search and rescue. Weighing less than a kilogram, its onboard camera records from a height of 150 meters. It's an eye in the sky that saves money and lives. Let's see how it works. The MD4 flies with the help of 4 fixed-wing rotors, each attached to an electric motor. You start it up, spin the blades, and up it goes. The design challenge is to keep the craft super light and whisper quiet, airborne and stable, all while transporting an HD camera. And to avoid losing it, program it to come home on its own when low on power, and land safely. When you tip the scales at less than a kilo, you don't need a big engine. That means less energy to fly and hardly any noise. To keep it light, designers chose carbon fiber for the MD4's body. A material born in the lab, made up of thin threads of carbon atoms in a hexagonal pattern. Weave it into fabric, create lightweight material with tons of strength. Small servo motors give the machine lift. All electric, without gears, the servos have more than enough power to fly the MD4. The 4-rotor platform keeps a horizontal and stable base in balance for taking pictures. That's the good news. But flying a quad rotor isn't like working a plane or a helicopter. 4 rotors means 4 sources of thrust, each needing constant adjustment. The motors are independently controlled by microprocessors that send and receive hundreds of signals to onboard sensors. The operator talks with the drone through a controller, sending FM radio signals that the MD4 converts into movement. To get a rock-steady hover, 2 rotors spin in one direction, the other 2 in the opposite. The 2 sets of rotors cancel each other out and keep the machine in a static position. If you drop the speed of one pair of rotors, the torque of the other 2 force the drone to spin. For a straight run, drop the speed of one rotor, which causes the leading edge to dip. Then you bump up power on the back rotor, and away you go. The machine gets all its power from a small rechargeable lithium battery, enough juice to keep it working for about 30 minutes. If the battery runs low during flight, sensors give the drone a pre-programmed flight plan to land it safely close to the operator, who just pops in a new one and sends it up again. And if the MD4 loses radio contact, onboard GPS puts the drone in park to wait for its master. If it doesn't pick up a signal in 30 seconds, it makes an emergency landing automatically. The GPS also allows a user to switch to autopilot for flying the machine on a predetermined route. These firefighters in Birmingham, England, use the MD4 to find deadly hotspots. Cops and security patrols sneak up on bad guys. And it inspects hard-to-get places for hydro crews. Flying around in silence with the latest cameras. It's a stable, floating platform for taking pictures, thanks to the quadcopter design that keeps the shot steady for as long as the batteries allow. If you're a softwood tree, between the ages of 50 and 80, live on a farm, and this machine shows up on your doorstep, you're in for a bad day. This is a feller buncher, a machine that revolutionized the lumber industry. And chances are, it cut down the wood that built your house and made your morning paper. It does the work of dozens of men, cutting up to 4,000 trees in a single day. One of these machines can clear about 100 football fields worth of trees in a week. All with the flick of a joystick. Let's see how it works. The feller buncher has 2 simple jobs: felling and bunching. Cut trees with a big saw, pick them up with a long, powerful arm, and set them down gently. First up, the blade. The feller uses a high-speed disc saw with indents to carry away wood chips, and teeth that are wider than the disc. If disc and teeth were the same width, pressure from the tree would sandwich the blade and the whole thing would grind to a halt. The teeth are made from carbide, a super strong alloy. Strong enough to rip through a ½ meter of dense, resin-soaked trees. The teeth cut through fibers inside the tree with these points. Then, rip out the weak middle section. As the tree is cut, it slides onto this holding plate. Without it, the tree's weight would freeze the disc and burn out its motor. Another great advantage of this machine is how low to the ground it can cut. Leaving behind big stumps wastes a lot of wood. And cutting low is more about reach than bite. Which brings us to the bunching part of this machine and its powerful hydraulic boom. The feller buncher needs distance from the trees to give its operator a clear view for a level cut, and to keep him and the machine out of harm's way. For that, you need a hydraulic arm that's strong enough to pick up and set down a 5-ton tree from 8 meters away. The hydraulic arm has 2 sections, the stick boom and the main boom. Getting these to work together is the key to success out here. With a single joystick, the operator moves and adjusts the boom's 2 sections to land in the right spot and make the perfect cut. Okay, you're through the tree. Why not just yell timber, let it go? Falling trees damage other trees. They're extremely dangerous. And out here, to be efficient, you need the wood out of the way. And neatly stacked for transport. To do all that, you need the hydraulic boom and its claws to be powerful, and you need a body that's not going to tip over. This machine's strong enough to grab several trees at once. After cutting, the operator closes the accumulator and hangs on while opening these clamp arms. When a second tree is cut, the accumulator arms are sandwiched between the 2. A double-hinged joint allows it to slip free and grab the harvest, while the claw is free to grab the next tree. Meanwhile, these special ends, called snouts, keep the blade from accidentally picking up forest debris and sending it flying off in all directions. As the claw grabs, the machine stabilizes itself. It floats on a leveling system that allows the machine to bob and weave on a series of hydraulic cylinders. It's kind of wrestling with the tree as it picks it up and sets it down. With a pivot point near the cab, most of the weight is back here. A great counterbalance to keep the whole operation upright. This self-leveling machine operates on slopes up to 45 degrees. Handy when you're working the side of a mountain. Its tracks provide a great grip without wrecking the forest floor. So tree farms like this one can be replanted. The machine's 31 tons are evenly distributed over 6.5 square meters. At any point, its heaviest impact is less than 5 kilograms per square centimeter. That's less than the pressure you put on the ground as you walk. When the feller buncher arrived on the logging scene in the 70s, it changed the industry forever. The old-style lumberjack is a dinosaur now, and a machine that looks like one replaced him. You're flying over rocks, river currents, and land without a hitch. It's what hovercrafts do. The HoverTech Rescue Craft is an emergency vehicle working some rough waters in Canada's Fraser Valley. When a call comes in, it's got to unload fast and launch in seconds from almost anywhere. Designers gave this machine just one fan and one motor. And that's a hovercraft rule breaker. A traditional hover has separate fans and motors, one for lift, one for thrust. To keep it compact and light, this machine's single engine does both. Here's how it works. When you start up, the fan blows air into an airbag or skirt made from heavy-duty nylon. Air pressure builds up to the point it has to escape, And the only way out is to push the whole thing up and blast out under the skirt's pockets. You're up and floating on a cushion of air. But you can't go forward on lift alone. At this moment, other hovercrafts need a second fan to move forward. That's because they don't have this. A splitter that divides the fan's air, directing enough downward for lift, while sending the rest out the back for thrust. When you're riding on air, there's not much friction. So all this machine needs is a 65 horsepower engine to hit a top speed of 70 kilometers per hour. You can go just as fast on a boat like this, but you have to push water out of the way and burn a lot more gas doing it. With a hover, you're more aircraft than boat. No current or tide can touch you. Transitioning onto land is no problem. The flexible skirt, made of individual air pockets, moves up and down with the terrain. And if one of its pockets rips, the one beside it fills the gap. And if that one rips, replacement happens fast, like everything else on this machine. For steering, the handlebars are wired to rudders. Navigating obstacles is no problem, and allows the hover tech to reach an emergency fast. But what if it needs to slow down and just, well, hover? A traditional hovercraft can shut its thruster fan and float on its lift fans, but with just one, it's kind of tricky. Kill that fan at full speed, you lose thrust, lift, and slam into the water. Here's the workaround. And it's an idea borrowed from reverse thrusters in fighter jets. These buckets swivel into the blasting air and redirect it forward. Reverse thrust. So no loss of lift or control. The buckets provide pinpoint control when approaching a target. Once in position, killing the fan lowers the deck closer to water. A high-density foam shell keeps it floating while this guy climbs aboard. When it's time to go, adjust the buckets to balance thrust while the fan gets up to full power. Then spin the buckets and away you go. Designers broke a few rules making this hovercraft portable and fast enough for search and rescue work. Pretty handy for guys on call 24/7. Part boat, part plane, the HoverTech gets to the scene fast in a business where every second counts. The latest trams generate electricity while braking and send it up the line to help power trams behind it. Flying a helicopter is a delicate balancing act between two rotors. But hauling tonnage and catching crooks takes a special breed. It looks like it can read our thoughts and predict our moves. The science behind the Segway transporter. This 3D printer is a real-world replicator. Feed it pictures, it manufactures objects in 3 dimensions. Let's take the lid off these machines and see how they work. Depending where you're from, this is a tram, a trolley, or a streetcar. Whatever you call it, the urban railway is making a comeback. At one time, almost all city transit ran on rails. But then, buses and cars took over. New technology, no emissions, and ease of installation has given this form of mass transit a new lease on life. Trams run on electricity, and the latest versions can actually generate some of their own power. Let's see how they work. Choosing low-emission trains over gas and diesel power is great for PR and government pocketbooks. But for this ride to appeal to the masses, you need more than that. To be number one in the public eye, you have to be efficient, reliable, and comfortable. Let's start with efficiency. Compared to other forms of mass transit like buses, trams need a lot less energy and maintenance. Their electric motors are more powerful, quieter, and efficient than their gas-guzzling cousins. Trams get power from overhead lines fed by the local grid through something called a pantograph. It draws electrical current through points of contact. Early versions of this device had a problem. Constant rubbing from overhead wires wore out contacts and cut off power. Now, overhead lines are laid out in a zigzag pattern. So the pantograph slides side to side while the tram is in motion, greatly extending the life of its contacts. Electricity flows from the wires to copper coils inside the motors. This creates a magnetic field that spins a magnet, and with it, the wheels. This machine can top 100 kilometers an hour, but rarely goes above 70 while working in cities. And that means it needs good brakes. But these ones aren't just for stopping. They also help feed electricity back into the system. A design feature that can save big on a city's power bills. When the machine needs to stop, the power is cut off to the motors, but the tram's momentum keeps the wheels spinning. And this allows the motors to generate power. It's called regenerative braking. The momentum spinning inside the motor creates an electric current that's sent back up through the machine, through its pantograph, along the overhead wire, and into the nearest tram. An electrical piggyback ride. And if the tram needs to stop in a hurry, it's also got sets of air brakes. In an emergency, say if something falls in front of the tram, the brakes all work together with a safety bar to prevent anything from getting stuck under the machine. Step 2 in winning over the public is reliability. And that means not breaking down. With no transmission, no potholes to deal with, no tires to go flat, and no fuel to run out of, the only thing that really threatens this ride is a power failure. Trams like these do cost a lot more to purchase than buses, but they last decades longer and cost much less to run on a day-to-day basis. Coming across as good for the environment and city bank accounts is fine. But it doesn't explain why the average person prefers light rail to buses. For that, you need to look at this machine's third advantage: comfort and style. New models come with street-level ground clearance for easy on and off. They can grow with extra cars to give plenty of rush hour elbow room. And with steel wheels that can be kept true, the ride is super smooth. The low ride comes courtesy of a design that hides most of the tram's components on the roof, giving the wheels and axles plenty of room to provide support. Super strong pivot points seamlessly join the cars together and enable these machines to take on up to 7 cars and still slide through corners. Accordion-like rubberized material fills in the gaps around the joints between the cars. It's rush hour, and now you have transit that's easy to board with continuous open space for over 200 passengers. Keeping a ride smooth has always been a challenge for machines that depend on steel wheels riding steel rails. And the wheels wear out fast, especially under a tram that has an empty weight of over 40 tons. So every 20,000 kilometers, they get a tune-up. A diamond-tipped truing machine. This big robot shaves off 0.5 millimeter thick strips until the wheel is perfectly clean and level. It guarantees a smooth ride and reduces friction, saving big on electricity. Fast, smooth, and cheap to run. With cities increasingly building more right-of-ways for the tram, the other options are looking a little older every day. Helicopters are hard at work all over the place these days. With great speed, range, and a lifting capacity of over a ton, machines like Eurocopter's Twin Star and B3 are fast enough to work for police, strong enough to haul for utility companies, and nimble enough to work in tight places without going down. These Hydro 1 pilots make it look easy, but flying a helicopter is anything but. Picture balancing on a large ball with a machine that weighs over a ton. To fly one of these, you have to control the 3 dimensions of pitch, roll, and yaw. Let's see how it works. An engine spins a rotor. The rotor spins blades, and up you go. A helicopter is an assembly of thousands of loose pieces trying to fly in formation. Getting them to work together to create the most versatile flyer in existence is the hard part. The first challenge is to create lift. The second is to control it. And the third is to keep it from crashing if the engine fails. First up, lift. The blades of a helicopter's main rotor are basically wings that slice through the air. They're shaped like the airfoils of an airplane wing. But these are much thinner and narrower because they have to spin extremely fast to get airborne. And to do that, they need a slight shift. This change in the blade's angle of attack, combined with their speed, forces air down. When the amount of air forced down overcomes the weight of the machine, it takes off. Helicopter blades need heavy air to create lift. The higher you go, the less air pressure there is, and the harder it is to climb. On to challenge number 2, control. Spinning the main rotor this fast is terrific, but it comes with problems. For starters, the body of the helicopter wants to spin in the opposite direction of the rotor. To control the machine, a precisely located counterforce is needed for balanced flight. And on a chopper, that comes from the tail rotor. On this machine, it's 1/6 the size of the main rotor, so it spins 6 times faster to balance the force from the big blades. The power for all this spinning comes from a high-performance engine that sucks oxygen into a combustion chamber to burn jet fuel. This produces super hot exhaust gases that drive a turbine. And it turns drive shafts that connect to the main and tail rotors. The drive shafts are linked through gears to a transmission that keeps everything in perfect sync. So now you've got basic control of a powerful flying machine. Let's take a closer look at some of the finer elements of helicopter handling. A twist throttle controls the engine power to the main and tail rotors. Once airborne, the rotors spin at a fixed RPM all the way. Pilots never hit the gas to go higher, faster, or to change direction. The fixed RPM is set to maintain perfect balance between the 2 rotors. A helicopter's ability to fly in 3 dimensions is all about the blades and their angle of attack. And that's controlled with the collective and the cyclic. They allow pilots to change course, altitude, and speed. The cyclic is the control directly in front of the pilot. which he uses to move left or right or to go forward or back. When you push the cyclic forward, the angle of the blades increases at the back and stay low at the front. This creates an imbalance of thrust and propels the craft forward. Same thing happens when you push the cyclic to the side. You get an imbalance of thrust and move sideways. The collective is located in the center of the cockpit. The pilot raises or lowers this control to go up or down or to change speed. And these signals stay in sync with all the spinning blades through the swash plate. 2 discs with a set of ball bearings in between them. When the bottom disc pushes up, its movement passes on to the spinning top disc. The more it's pushed, the more the swash plate pushes up each rod, changing the angle of attack for each blade. While all this is going on, pilots use foot pedals to control the angle on the blades of the tail rotor. All the forces applied to the main rotor blades have to be counteracted. Collective, stick, foot pedals. A very delicate balancing act that keeps everything from spinning out of control. On to the third challenge, staying in the air when something goes wrong. What happens if the engine suddenly conks out? If you figure it just drops like a stone, you'd be wrong. To fly one of these things, you gotta learn to land it when the engine quits. And they pull that off with auto rotation. If they lose power, pilots let the main rotor spin freely. The blades are flattened out to catch max air, and this usually provides enough control to glide safely to the ground. Remember the thousands of parts bit? Well, some are more important than others. If you lose your connection with the blades, you're gonna drop like a stone. There's no backup plan for this malfunction. On helicopters, that comes down to some very important nuts, the main thing keeping the blades attached to the machine. But losing them is never a problem on well-maintained machines like these. When you put a great helicopter in the hands of a crack pilot, there's nothing to fear. Just enjoy the ride on the most maneuverable flying machine in the world. Since its unveiling in 2001, the Segway has captured our imagination and pointed to the future of transportation. That's because this machine seems intelligent, impossibly keeping us balanced while mysteriously reading our intentions when we want to move, stop, and turn. No, it's not magic. But that doesn't take away from the cool stuff that goes on inside when you ride this thing. Let's see how it works. The Segway is an electric scooter with lateral wheels. So it's a machine that has to copy what we bipedal humans do and learn to stay in balance. As you lean forward, gravity wants to take you down. And it would, except the Segway's wheels automatically pick up speed to keep the platform beneath you. Same goes for reverse. Lean back, and that's where you go. The wheels have to spin in that direction to keep you from hitting the ground. So, from the moment you step on the Segway to the moment you get off, you're basically falling. Even when keeping it stationary, you're really falling forward one moment, backward the next. The wheels keep catching you before you hit the ground. Balance and movement are the same thing on this machine. So how do the wheels know what to do? To help keep us upright, the human machine comes with legs, muscles, and a brain. Same goes for the Segway, in the form of wheels, motors, and a really clever little box that's crammed with sensitive measuring devices. 5 angular rate sensors detect changes in direction and speed, and tilt sensors detect angles. They work the same as a carpenter's level, except the liquid inside conducts an electrical signal. Together, these sensors provide data that allow the machine to determine if you're about to tip over. It sends the commands to the wheels and keeps you upright. No matter which way you lean, they're always one step ahead of you. The Segway has 10 microprocessors, giving it about 3 times the brain power of a typical PC. You can't outsmart this machine. To turn, push the control stick to one side. This decreases power to the inside wheel, spins the outside one faster, and round you go. Segways have a carrying capacity of up to 118 kilograms. Each wheel comes with its own 2-horsepower emission-free electric motor. Gearboxes inside the wheel assembly step down the motor's RPM for smooth control and a distinctive whirring sound. The gears also help limit the Segway's speed to about 20 kilometers per hour. But even at that rate, you'd do some damage if something went wrong and you flew over the handlebars. So the machine comes with backup systems that shut it down safely if there's a glitch. There's no tumbling off this guy. When you're done for the day, just ride over to a wall socket, plug it in, and in no time, it's ready to ride again. And these days, that includes everything from off-road trail riding to making a day of foot patrols a little smoother for police. This machine may not rule our sidewalks yet, but it's finding a way into our transport systems one lean at a time. This is the Z-Core Spectrum 510. It's technically called a 3D printer, but we're going to call it a replicator. This machine that looks like a photocopier prints objects in 3 dimensions. Simply upload a digital picture to get a solid object up to a cubic foot in size. Let's see how it works. This machine makes anything, from action figures, architectural models, inventions, even a prototype running shoe. And they all come from exclusive design software that speaks the printer's language. In this case, an online gamer wants to take his action figure from virtual to real. To start, feed the printer with a digital 3D file. The printer's processor dissects the 3D image like a CAT scan, slicing it into super thin layers, about 1/5 of a millimeter each, close to the width of a human hair. The shape of each virtual slice is translated into mathematical coordinates and plotted out, a bit like how GPS uses math to build virtual maps. Once the design is loaded and analyzed by the printer, the replicating can begin. A roller moves a thin layer of powder from a feed bin into the printer's build chamber. The powder is a mix of plastic compounds that have to be of a certain hardness and elasticity. When dry, it has the consistency of talcum powder. Once the first layer of powder is laid down, the print heads go into action. They lay down color ink onto the first layer according to the object's coordinates. But this machine doesn't just lay down ink. To build in 3 dimensions, it needs an adhesive or binder fluid to start the foundation for the final object. Layer after layer, they're glued together. The build chamber lowers with each pass, and the next thin layer of powder is added, ready for more ink and more adhesive. This continues 1 layer at a time until the entire model is complete. The object's color is created by mixing 3 primaries of ink held in these reservoirs. That sends them out through 3 print heads. While a 4th carries clear binder fluid. This allows the machine to create white when necessary. Here's a completed print job. It comes out as a thick block of powder, but watch as the powder is blown away. Buried inside, solid figures. The surrounding powder holds up the objects as they're being constructed. The excess stuff is reused for the next printing. Nothing is wasted. Like an archaeologist wiping away the dust on an artifact, our newly printed subject is revealed. The figure gets a once-over by hand and is dunked in sealant and dried. One of these printers can crank out about 16 of these every 5 hours. Imagine how long it would take to make these by hand. Architects and engineers use this machine for everything, from scale models to machine prototypes with parts that move. If a regular printer is a painter, the 3D printer is a sculptor. And a version of this may be in your home soon enough. If you can imagine it, this machine can make it.